The topic of discussion is the bias versus variance trade-off that is normally observed during model selection. So the model selection is a process of fitting a best possible curve that is passing through the data when we are dealing with a linear regression problem, or could be finding out a boundary that is separating two or more class of samples. So that is normally seen in classification problems. So just for our understanding, we only consider the case of linear regression here. So here normally in linear regression, we are normally given a set of examples, x comma y, and so we need to find the best possible fit that is passing through all these points in the best possible way. So here as we can see right away that y is equal to x square represents the ground reality. That is, this data was somehow generated from a quadratic function y is equal to x square. But normally the designer doesn't have access to the ground truth usually. So in trying to fit the set of examples which is shown with the green pluses, the modeler tries to fit data, and as we can see there are infinity possibilities of such models that we can fit here. For example, two such models are so let us call this as model 1 or curve 1. And the second type of model could be basically a curve that is more flexible while it is passing through the data. So let us call this as curve 1, curve 2. So these are the two possibilities, curve 1 and curve 2, which actually give us the two possible fits of this data, of this training data set. So here, as we can see, the curve 1 is basically the simplest form of the explanation. That is inflexible and has lesser number of degrees of freedom in trying to fit this data. But the curve 2 is more flexible, so as it fits the data, so hence gives us a more complex function. So curve 1 is more complex. Curve 1 is more complex. Curve 1 is simple, or it is basically a linear function or a linear model. And it is inflexible. Similarly, the curve 2 is more complex, is nonlinear, more complex, and has more degrees of freedom. So as it is trying to fit the various changes in the data, so it has more degrees of freedom. and here less degrees of freedom. Okay, so these are our two choices. Now here obviously when you have a model that is y hat is equal to some f hat of x, that is an estimate of output variable, an estimate of the output variable y hat is equal to obtained by substituting x values into our model f hat. We normally define the testing error. We normally define the test error as the expectation of difference between the true label or the true output variable and the estimated variable square. In trying to judge the performance of these two competing models, normally we calculate the test error. The test error is defined as the expected or the mean value of y minus the y estimate square, expectation of y minus y hat square. So obviously the model that gives us the lowest test error is considered to be a better model. So now we can actually show a small proof that we can prove that the test error, which is the test error at any point x naught is tested at any point x naught is expectation of y minus f hat of x naught whole square is equal to the bias of the model f hat of x naught square plus the variance of the model f hat of x naught plus the variance of the irreducible error. To the modeler, the variance of the irreducible error is whereas the bias and the variance of a model can be controlled through proper modeling. So what is basically a bias of a model? So if you consider the curve 1, the curve 2, a much simpler model is used to fit an actual more complex model such as y is equal to x square. The error obtained, this is known as bias. Similarly, in the case of case 2, a more complex function is used in place of the ground reality, which is y is equal to x square. And hence, such a function has more degrees of freedom, and the variance of this function is also very large. So as such a function is applied on the, if this such a function is applied on the testing set, probably because of overfitting the training set, it may not do a good job on a testing set. Here often the modeler has to choose something in between, a model that is not as much simple and also a model that is not as much complex. Let us consider this graph. So consisting of flexibility on the degrees of freedom of a model on the x-axis and the testing error on the y-axis. So here the dotted line shows the error due to the error from irreducible error, the variance of the irreducible error. No matter how good we can do, our testing error cannot be lesser than, it cannot be below this dotted line, because so from equation 1, both the terms, the bias squared and the variance square, are both positive terms. Hence, the total error cannot be below the variance of irreducible error, below the dotted line. Now, so in plotting the flexibility of a model versus the testing error, we obtain a convex shaped curve as shown here, where for smaller degrees of freedom or lower flexibility, the bias plays a major role. The bias is high. For such a model, the bias is high and the variance is low. Similarly, for higher flexibilities of the model, that is higher degrees of freedom, the bias is low, whereas the variance can be very high. So in trying to optimize these two factors, one can choose a more modest model that is not too rigid and also not too flexible, such that the total error is minimum. So such a phenomena of trying to balance the bias of a model with the variance is known as the bias variance trade-off. Thank you.